All right, guys, here we go. So let me sort of lay out the day for you. So you guys are telling me, especially because of your great homework scores, that you are very, very comfortable with drawing Lewis dot structures. And guys, we've gone through 2 homework assignments of these. We've had lots of practice. You got all your questions answered. We're good to go. So guys, what we're going to do today is we are going to take these flat, lifeless, not completely accurate Lewis dot structures, and we're going to turn them into these. And we're actually going to figure out what these things look like 3-dimensionally. And what you're going to find out is the bridge to their 3-dimensional structures is being able to count their shared and lone pairs. So guys, in the last 2 homework assignments, we've actually had you counting shared and lone pairs. The reason is going to become very evident today. So if you can count shared and lone pairs, and if you carefully fill out the double top secret decoder key, which will be, go ahead and look at it, on the back of your homework or on the back of your notes page, guys, you're going to be able to figure out these 3-dimensional structures. Because if you allow your eye to scan down this page, look at how it's organized. So up here at the top, it says 4 electron domains. You're going to find out in a minute that electron domains are shared and lone pairs. Then you look down at the table, you'll notice that we've got bonding pairs and non-bonding pairs. That's how to know. Then if you go down to the next table, it says 3 electron domains. Again, the electron domains are the shared and lone pairs, and then depending on how many are bonding and how many aren't, it tells you the structure, and that pattern just keeps going. So guys, if you can figure out how to count shared and lone pairs, and you already seem to know how to do that, you're going to be very successful with this. It goes really well. So here's how this is going to go down. The entire front of this, go ahead and flip it over. Guys, the entire front of this is terms and definitions. And again, the deal I'll always make with you, if it's not on here, even if it's up here, you don't need to write it down. So guys, we're going to start by doing terms and definitions. Then when we're done with that and we have all of these understandings, we're going to jump back here, and by filling out this decoder key, you're going to be able to take all these Lewis dot structures and figure out their 3-dimensional structures. And then guys, when we're done with that, you'll have time to work on some more of these. And then when I see you on Thursday, you're going to actually get these model kits, and you guys are going to be building these and drawing them and getting your hands on them, so to speak. Get the idea? So guys, that's the deal for today. So let's transition. Again, you don't need to write this down. So guys, this is where we're at right now. We have done Lewis dot structures, but you've noticed that these are 2-dimensional. They are all very, very flat. They don't live in 3 dimensions, and molecules do. So what good are they? Well, guys, these representations tell us a lot of things. They tell us the order that they bond. They tell us the types of bonds that form single, double, triple, but they don't tell us what these look like 3-dimensionally. So that's what we're going to do today. We are going to push into 3D. So Maddie, I didn't make this connection. You're going to like, because you're graphic design, I just found out this morning that Maddie wants to be a graphic design person. You're going to like this because you probably think very spatially, and so this is going to be good. So guys, if you're a spatial, visual kind of person, this is going to be a great thing. But guys, to get started, we got to start with terms. This is where you want to start taking notes. So guys, the terms that you need to know are these. First of all, the term electron domain. And guys, we sort of alluded to this when we looked at the back of the page, and you've got space for this in your notes. But guys, an electron domain is defined as the space that electrons occupy around the nucleus of the atom. You'll notice there's a little tick mark for that. Now guys, don't write down the next bullet point because I've already given it to you. So here's where we are. Electron domains are the spaces that these things, the electrons, occupy. Now, there can be 2 types. Bonding domains and non-bonding domains. But you'll notice I already gave those to you in your notes, so now we just need to talk about what they are. So guys, bonding domains are the shared pairs. So down beneath bonding domains, you can just write out shared pairs. Because this next point you don't need to write down because I'm going to show you what it means. So when we say shared pairs, guys, the thing that's a little different is this. Any type of bond can count as one domain. You don't need to write it down because I'll show you what that means. So what then are the non-bonding domains? Well, guys, the non-bonding domains are the lone pairs, and you'll notice you've got a line to write that down as well. So here's what we know. What is an electron domain? It is the space that electrons occupy. There are two kinds. There are bonding domains that are the shared pairs. There are non-bonding domains that are the lone pairs. And guys, remember, you for the last two homework assignments have been counting shared and lone pairs. Without knowing it, you were actually counting domains. But we've got this weird idea that any type of bond counts as one domain. So let me show you what that means, and there's room for you to write this down. So guys, these are all individual domains. So a lone pair of electrons is a domain. A single bond is a domain. A double bond is a domain. And a triple bond is a domain. Because, guys, the word domain just means the space where you find something. And it doesn't matter how many somethings you find. Could be a lone pair, could be a single bond, could be a double bond, could be a triple bond. It doesn't matter. They all count as one domain. And again, I gave you space to draw that. But that's what this is talking about, this idea that any bond can count as one domain. So each one of these is a domain. So, guys, that's big idea number one. Do you have questions? You understand what a domain is? You're sure? Okay, then prove it. Don't write this down. Remember this guy? The molecule that you have to memorize? Yeah, this is your guy. So guys, don't blurt it out, but take a look at this carbon and think to yourself, how many domains are on that carbon? Don't say it. Let's let people think. But now let's talk about it. Guys, how many domains are on that carbon? 4. They are all single bonds, 1, 2, 3, 4, and there are 4 domains around that carbon. You'll find out in a minute that that means that it's tetrahedral, because tetra means 4. Then, guys, what about this carbon? Be careful. How many domains on that carbon, given that it's a little different, how many domains? Is it 3 or is it 4? Well, guys, we know that these are domains, right? 1 and 2, but what about that? It's one domain. It's a double bond, but it's still one domain because it's one location where electrons are. So this is 3 domains. You're going to find out in a minute that this is what is called trigonal planar, because tri means 3. You'll see in a second. Now, guys, what about this oxygen? Now we've got lone pairs. How many domains? 2 or 4? 4. We've got 1 and 2 that are bonds, 3 and 4 that are lone pairs. This has got 4 domains. You're going to find out again in a minute that this is tetra, which means 4-hedral. So this is tetrahedral. You guys good on those? Now this is the tricky guy. What about this oxygen? How many domains? You sure it's 3? Let's count them. Here's a domain, here's a domain, there's a domain, 3 domains. Are you satisfied now that you understand domains? You're good? Okay. So now, guys, moving along and continuing this conversation about domains. The next thing we need to talk about is, what do these domains do to each other? And the answer is that they vesper. Did I give you that in the notes? Oh, look at me. Okay. So, guys, obviously vesper is an acronym, right? So what does it stand for? It stands for the valence shell electron pair repulsion theory. But I don't know why they call this a theory, because it's actually not just a theory. It really happens. I always thought that theories were supposed to be ideas that we're not sure about. We're sure about this one. So guys, we now understand what domains are, but the question is, what do domains do to each other when they get around the nucleus of an atom? And the answer to the question is, they vesper. They valence shell electron pair repulsion. So what does that mean? Well, you ready? Guys, what are valence shell electron pairs? Those are the domains. See, guys, these 4 words, valence shell electron pair, just means domains. I wonder if my board will let me do this. I just got approved for a new board. Huh? You want to guess how much a board costs? Take a guess. Ooh, little low, little high. $1,700. Yeah, ridiculous. And they want $310 to install it when all it takes to install it is just lift the stupid thing up and put a new one in its place. If you want to make a lot of money, sell stuff to schools. Okay, so here's what this means. These guys right here, these are the domains. If you want to write that down, you certainly can. So guys, these valence shell electron pairs, and you've got to forgive my writing. This is really, guys, the best I can do. So guys, these valence shell electron pairs are the domains. So what does it mean that they repulse? What do they do? What does repulsion mean? They're pushing each other away. And guys, why would the domains push each other away? They're all negative. They're all electrons, and they don't want to be around each other. So what they do is they push on each other, and they get away from each other as far as possible. So guys, we describe that this way. It simply means that the electron domains repel each other. And the thought then, guys, is that this repulsion causes these domains to get as far away from each other as they possibly can. And that's what gives them their three-dimensional structures. They are not flat. They are not two-dimensional, because when they push on each other, they get as far away from each other as they possibly can. And that gives them their crazy three-dimensional structures that we're about to talk about. So guys, while you're writing this down, let's sort of review where we are. First of all, now we know there are these things called domains. There are two types. There are bonding domains and there are non-bonding domains. And you guys are really good at counting and identifying them because we trained you to do that over the last couple days, having you count shared and lone pairs. Then guys, we found out that the Vesper theory is in action. These domains push on each other, and when they do, they get as far apart from each other as they possibly can. You good with thought number 2? Okay, here comes the last thought, thought number 3. Let's ask the question. Guys, how many different kinds of domains are there? 2. Bonding domains and non-bonding domains. And guys, what you've got to know is that these are not the same size. Bonding, and there's nowhere for you to write this down, but guys, bonding domains and non-bonding domains are not the same size. So you'll notice that that's the next points in your outline is bonding and non-bonding domains, and you need to understand their sizes. So let's talk about bonding domains first. Guys, bonding domains are long and skinny. The reason that they're long and skinny is because they're being pulled on by 2 nuclei. So guys, I'm going to steal this from you for a second. I'm going to change this. It's going to be a pain. Never mind. That's not going to work. Oh gosh, come back. There we go. Okay, so guys, bonding domains are long and skinny because they're being pulled on by 2 nuclei. Then guys, non-bonding domains are short and fat because they're only being pulled on by 1 nuclei. And I know that's a little bit vague, so I'll show you pictures, and once you're comfortable with this idea and everything that you just learned about domains, we're going to flip this paper over and we're going to fill out the decoder key. And then guys, we're going to give you a chance to play with these. And then on Thursday, again, your hands will really get dirty and we'll give you the model kits. So guys, what does this mean? Well, here's the idea. When you picture a bonding electron domain, picture this. And guys, if you'd like to write that down or draw it, I gave you space over here. So if you want to draw, just so you have sort of the visual reminder, guys, this is actually kind of what a bonding domain looks like. You've got the nuclei of the 2 atoms that are bonded together, and then this blue region represents that shared pair of electrons that creates the covalent bond. Remember, we're comfortable with clouds and the idea that electrons exist like clouds. But guys, a bonding electron pair this is what we call long and skinny. You're like, wait a minute, that doesn't look very long and skinny. Well guys, compare it to this. This is what a non-bonding domain looks like. It is not involved in a bond, so there isn't another nucleus over here pulling it, and so as a result, it's short and fat. So non-bonding domains, short and fat, bonding domains, long and skinny, even though this doesn't really look long and skinny, but obviously it is compared to that, which is a non-bonding domain. So here's what we got. Domains are the places where we find electrons. These things can be lone pair, single bonds, double bonds, triple bonds. And then, guys, we found out through Vesper that these domains push on each other. They get as far away as they can. And when they do, that gives them their three-dimensional structures. And now we know that bonding domains are long and skinny, and non-bonding domains are short and fat. How'd we do? You guys good? Thoughts, questions, concerns, things you want to talk about before we do the decoder key? You really good? All right, flip them over. Here we go, guys. We are now going to take everything that you figured out about electron domains, and we are going to use these ideas to create three-dimensional understandings of what these molecules look like, and do a little bit of extra credit. Guys, this is going to be your last extra credit opportunity for the quarter. Okay, but I'll show you what it is in just a second. So guys, here we go. Don't try to write any of this down. There's not room for you. Well, there's not room for I'll tell you when to write stuff down. But guys, it goes like this. A question for you. We are now going to talk about atoms with 4 electron domains. And guys, you'll notice that I wrote that down for you at the top of the paper. 4 electron domains. Okay, so here's the question. When 4 objects, and by the way, this is also the extra credit question. You can answer this question mathematically for extra credit. It's due the day of the test. So, when 4 objects surround a central point, and these 4 objects are domains, but anyway, when 4 objects surround a central point, what angles are created if these objects are as far apart from each other as possible? So let me show you what I'm talking about, assuming that my pen will allow me to do this. Oh gosh, didn't work. Hold on. Come. Hey, there you go. So let's talk. Okay, so guys, the idea is this. Here is, come on, baby. Oh, good. Okay, there's our central point. And let me draw a circle. Oh boy. All right. Wow. Huh? It's an egg. Okay. It's not even an egg. All right. So guys, 4 points. You ready? So here's 1 point. This is our central point. Let me even change colors if it'll let me. So guys, here is 1 point. Where would I put a second point to get it as far away from that one as possible? Down here, right? But we're not talking about 2 points, we're talking about 4 points. So where do I put the other 2 points to get them as far away from each other and the 2 points that are already there? Left and right, right? So we'll put one here, and we'll put one here, and we will connect these lines. And what is the angle that is formed at the intersection of those lines? 90-degree angle, right? So, given this drawing, it would appear that the answer to this is 90 degrees, because each of these points is as far away from the other as they possibly can get, and that would create 90-degree angles. So guys, why is the answer to this question not 90 degrees? It appears to be 90 degrees. So why is the answer to this question not 90 degrees? Because molecules aren't two-dimensional. Guys, if we lived in a two-dimensional world, the answer to this would be 90 degrees. But we live in a three-dimensional world, and in a three-dimensional world, the answer is not 90 degrees. So guys, let me show you what the answer actually is. You ready? Make the connection. Do you see it? What does this pyramid have to do with the question that's on the board? How many points does this pyramid have? 1, 2, 3, and then the one that's in my hand. You got it? There's 4. So guys, if these are the 4 points, where is the central point? Right here in the middle. You get the idea? Okay, now, And I'm going to move this because I'm going to make a mess out of this if I don't. No, we're good right there. Okay, so guys, here's our central point right in the middle, right? Now, the other thing that we've got to verify before we can use this as an example is we've got to verify that these 4 points are as far apart from each other as they possibly can be. And guys, I can guarantee you that these 4 points are spread out as much as they can get. What did I do when I made this to guarantee that these 4 points can't get any further apart? What did I do when I made this? Really? Exactly, Cody. All the straws are exactly the same length. What I did is I took a fistful of straws, tapped them down flat, cut them all off, and because these straws are all the same length, we now understand that these points are as far apart as possible. Guys, understand I don't hold you responsible for not knowing. We have so gutted geometry in high school that you guys are now geometrically illiterate. Okay, so these things are as far apart from each other as they possibly can get. Now, guys, let's do this. Let's take this idea and let's connect it to what we're talking about. So in here, guys, all I've got is bubble juice. The stuff that you use, dip it in there, blow bubbles. And you got to really get this lubed up for it to work. Here we go. Right there, right there. Come on, baby. Wow, I may have to soup this up a little bit. It's settled. Come on. Huh. Let's do it. Oh, there. Maybe I just need to go slower and let it really get gooped up. Are you not going to go? I may have to just pour some more. Oh, there we go. Do you see it? Guys, there's our central point. And that central point is being connected to all these other points. And if you look at that angle, can you see that that angle is not a 90-degree angle? Do you see it? So guys, what is this? Oh, what is this? I can't walk around or it's going to pop. What does this have to do with the conversation that we're having? Well, guys, these 4 points are spread out as much as they possibly can get, and we've got the central point in the middle. And if each of these points represents a domain, they are getting as, well, they are as far apart from each other in the same way that domains get as far away from each other as they possibly can. And you can clearly see that in 3 dimensions, that is not a 90-degree angle. Is it smaller or larger than 90 degrees? It's larger than 90 degrees, right? And so, guys, we actually know what that angle is. And you know that I already accidentally put it up. But, guys, that angle is actually 109.5 degrees. And you'll notice that there's a place for you to write that down right there where it says angle. So, guys, the idea is this. If you have 4 objects, if you have 4 domains, and they are spread out as far as they possibly can, just like we did with the bubble juice, the angles that they form are not the 90-degree angles that they would be in 2 dimensions. In 3 dimensions, they're actually 109.5 degrees. So now let's call time out. For extra credit, prove it. For extra credit, prove that when you spread 4 objects, 4 points around a central point in 3-dimensional space, the angles that are created are 109.5 degrees. And guys, I've seen 4 different ways of doing this proof. You can do it using the law of cosines. You can do this using matrices. You can do this with a geometric proof. And you can actually do it with trig without using the law of cosines. But you can use tangent, but it's a little more cumbersome. So guys, if you would like extra credit for this, your challenge is to prove that these angles are 109.5 degrees. Now guys, let me just be straight with you about this. You can Google it and you'll find the answer. Here's the trick. You don't get credit for turning it in. You get credit for teaching it to me. So what's going to happen, guys, is these are going to be due next Monday, the day of the test. And I'm going to gather up, you're going to write all of this out. You're going to give me everything that you've got in terms of proving that this is the case. And then what's going to happen is the day after the test, we're going to have a short day of class, hopefully. But if it's not, then it'll be shortly thereafter. Guys, we'll have a day where you guys will be working on homework, and what I'll do is everybody that turned in the extra credit challenge, you and I will go next door one-on-one, and you will teach me how it is you figured out that the answer is 109.5 degrees. And you don't get credit for it unless you teach it to me. Do you get the idea? So if you're interested in doing this, the answer is 109.5. You now see why relative to the bubble juice, but guys, understand that we can prove it mathematically, and I'd love for you to do it if you want extra credit. You get the idea? Okay, so whether that's the case or not, we now need to name this thing. So guys, what is the geometric term that we use for 4 that isn't quad? Tetra. So these are what are called tetrahedral structures. All right, so now guys, go down into your table. You got your table right there? And here's what you're going to do. We are going to populate this table with a bunch of tetrahedral molecules. These are the ones that we're going to do. Write them down. CH4, NH3, H2O, and HF. What do these all have in common? The thing they all have in common is 4 electron domains. But what you're going to find out is these molecules don't look anything like the others. They all look different, even though they all have 4 electron domains. So guys, the next thing you got to do is move to the right and draw their Lewis dot molecular structures. I'll give you a second to do it. Actually, better yet, you've already done all of these. Here they are. Guys, these are the Lewis dot structures for these 4 molecules. So guys, as you're finishing writing those down, if you allow your eye to scan to the right, you'll notice that the additional things that we're going to talk about is the number of bonding domains, the number of non-bonding domains, and then the angle in the name of each one of these molecules. So once you've drawn down the Lewis dot structures, you're ready to go, and we're just going to work our way to the right, talking about what these molecules actually look like. You guys got them all written down? Okay, so guys, do this with me. Ready? Look at CH4. How many domains on the carbon? 4. Look at NH3. How many domains on the carbon? 4. Water. How many domains on the oxygen? 4. Hydrogen fluoride. How many domains on the fluorine? 4. That's the point. All of these have 4 electron domains. So what's the difference? Only in CH4 are all of those domains bonding domains, and every time we move down, we've got 1 fewer bonding domain and 1 more non-bonding domain. Do you see the pattern? So now let's work across. So guys, how many bonding domains in CH4? 4. How many non-bonding domains in CH4? None. So guys, what does that tell us? Well, guys, that tells us that all of the domains are bonding domains, and this dude looks like this. This is a CH4 molecule, and for those of you that are really tuned into this, you may have even realized that this is a mess, that this is our pyramid. You get it? Guys, that is our tetrahedron. That is our pyramid. So guys, if this is our pyramid, then what is the angle that is in CH4? 109.5 degrees, and we already know the name of that. It is what is called tetrahedral. Yes. Messy, messy, messy. All right. So you guys good on CH4? Now let's do NH3. So guys, NH3, how many of these 4 domains are bonding domains? 3. How many of these 4 domains are non-bonding domains? 1. So guys, now this gets a little different, because this is actually what NH3 looks like. You've got the blue nitrogen, you've got the 3 white hydrogens, but guys, what is not represented in this model? The non-bonding pair of electrons. Now guys, think, and if you need to flip your paper over, you can do that. Guys, what do these bonding domains look like? Are they long and thin or short and fat? The bonding domains are long and thin. But what about the non-bonding domain that's up here that isn't even represented? It's short and fat. Now guys, watch really close. Watch my fingers. So these angles start at 109.5 degrees, right? But here's the thing. This non-bonding domain is short and fat, and it pushes down on the bonding domains. So this short, fat domain goes and it bends these down. So what happens to that angle? Does it get bigger or smaller compared to 109.5? It gets smaller. So guys, the angle in this structure is less than 109.5. We already identified one non-bonding domain. It's less than 109.5. It's actually 107 degrees. Because you don't need to know that. They wrote it out of the AP curriculum, so we don't teach it anymore. But it's actually 107 degrees. Now guys, here's the trick. This ain't a tetrahedron, is it? If you look at this thing, this is not tetrahedral. So we've got to name it. So guys, how many legs does it have? 3. What's the word for 3? Tri. Now guys, look. Can you see that it kind of looks, oh gosh. Can you see that it kind of looks like a pyramid with 3 legs? So guess what we're going to call it? This is what is called a trigonal pyramid. So anytime you have 4 domains and 3 of them are bonding, you will have what we call a trigonal pyramid. You get the idea? Now let's do water. Of the 4 domains on the oxygen, how many are bonding in water? 2. How many are not bonding in water? 2. So now let's look at a water molecule. Guys, water looks like this, right? But what, again, is not represented here? The 2 non-bonding domains. So guys, remember, these non-bonding domains are big and short and fat. And what do they do to these guys? Push them away, and the angle gets even smaller. You don't need to know it, but it is actually 104.5 degrees. All that you need to know, though, guys, is that the angle is less than 109.5. So, 4 is tetrahedral. 3 bonding domains is trigonal pyramid. What are we going to call this structure with 2 bonding domains? Bent. You want to know why? Because it's bent. Huh? Bent? Bent. All right. So now, guys, the last one. Bless you. Take a look at the fluorine. How many bonding domains are on the fluorine? 1. How many non-bonding domains are on the fluorine? 3. So take a look. What, and the fluorine is the green guy. What is not represented in this structure? 3 non-bonding domains. And what does that do to the angle? Nothing, because there isn't an angle. Guys, look at what's in my hand. You know enough about geometry to know this. 2 points do not define an angle. What do they define? A line. There is no angle. So guys, the angle is undefined. There is no angle. And what are we going to call a line? We call this line straight. You good? All right. So guys, please don't try to write down what I'm about to share with you. But in summary, here is what you just learned. What do all these molecules have in common? They all have tetrahedral domain geometries. And you've got to be able to identify that. All of these have 4 domains. So their domain geometry is tetrahedral. Then their molecular geometries, which are the tetrahedral, trigonal, pyramid, bent, and straight, their domain geometries depend on how many of those domains are bonding and how many of them are not bonding. You get the idea? Okay, let's go 3 domains. So guys, same question, but this one's not worth extra credit. Here's the question. 3 objects, 3 domains, 3 objects around a central point. What is the maximum distance we can spread them out? So there is, oh gosh, there's our central point. Wait for it. That is a fine circle. Well, wait, I can't even rate. Don't laugh. Oh, there. Okay. Huh? All right, so here we go, guys. 3 points around the central point. So I can put 1 point there. Now, what if I want to put these other 2 points as far away from the others as I possibly can? Can you picture it? Yeah, we'd go 1. Crap. Come back. Okay, here we go. So we could put one of them there, and we could put the other one there. And when we connect the dots, we end up with this. And guys, please tell me you know what that angle is. 120 degrees. How about, what's a whole circle? 360 divided by 3, 120 degrees. Now, this is 2-dimensional, right? What if we make this one 3-dimensional? Doesn't change. You can't spread them out anymore, even when we think of this in 3 dimensions. This is 3 dimensions. There's nowhere else for them to go, because if we pick this up out of the board, it's actually getting closer to the other ones through this plane. You can't spread them out anymore. And so guys, the answer to this question then is 120 degrees. Now, what are we going to call something that is, well, let me just bring this back. What are we going to call that? So it's tri, right? But here's the trick, gang. These are all flat. They are all in the same plane. So we call this trigonal planar. So now let's look at a bunch of molecules. Well, 2. Let's look at molecules that have trigonal planar domain geometries. So moving down to our table, we are going to do CH2O and NO2-. And guys, you've already done these in homework. Actually, you've done the NO2 twice. And they look like this. So just go ahead and write them down. So guys, you'll notice that on the NO2, I drew it a little differently. You wouldn't be asked to do this, but I drew it representing the 120 degree angles. Again, you'll never have to do your Lewis dot structures accurately like that. But guys, let's make sure we understand what we're looking at here. I'll give you another second to draw them, and then we'll talk about them. Yeah? Yeah, you know what? It should be, but I didn't put it there. I actually, when I originally drew it, I put the brackets on it, and it just got cluttered. Is that distracting that it's not? Yeah, but it should be. Maybe I should put it there just and deal with the clutter. So guys, take a look. How many domains are on this carbon? 3, right? How many domains are on this nitrogen? Are you sure? So 1 domain, 1 domain, 1 domain. So that's the point, right? Both of these molecules have 3 domains on the central atom. And that's why they're a part of this group, because they have 3 electron domains, which means their domain geometries are trigonal planar. Now let's look at their molecular geometries. Looking at this guy, how many of those 3 domains are involved in bonding? All of them, right? Single bond, double bond, all 3 are involved in bonding. How many of the domains on the carbon are non-bonding domains? None. And guys, it looks like this. Double bond to the oxygen, single bonds to the hydrogens. So guys, what are these angles in here? 120-degree angles, right? So they're all involved, and you can even see that it's planar. Isn't that cool? You can see the 3 angles, you can see they're all 120, and you can see that it's planar. The double bond makes it flat. That makes this thing planar, and we call this a trigonal planar structure. Now guys, let's take a look at NO2. So in NO2, how many of those 3 domains are bonding domains? Just 2. How many are not involved in bonding? 1. So guys, it looks like this. You've got a double bond to an oxygen and a single bond to the oxygen. What's not represented up here? The unbonded electron pair. What does that short, fat, unbonded electron pair do? Squishes this down. Where does that angle start? Not at 109.5. Where does this angle start? 120. So what will the angle be now? Less than 120. Now guys, we've got to name this critter. What are we going to name this dude? What's it look like? Bent. It's bent again. This is also a bent molecule. Now guys, some of you may be thinking to yourself, wait a minute, isn't something missing? What's missing? We're really not done. Yeah, what about the example of there's 1 bonding and 2 non-bonding? Why did I not include it? It does happen. Why didn't I include it? Because guys, if there's only 1 bond, that means there's only 2 atoms, right? And if there's only 2 atoms, same as before, that is a line and not an angle. So guys, if we add 1 bond and 2 non-bonding pairs, the angle would be undefined, and that would also be straight. So I didn't include it because anytime there's 1 bonding pair, there is no angle, because 1 bond only connects 2 points. So if there was, and I sort of wrote this out here, notice that I left off the example of 1 bonding domain, because if there's 1 bonding domain, the angle is always undefined and the name is always straight. So if you want to sort of write that down and go 1 and 2 and then just undefined and straight, it's always the case. So I just left it off. Now guys, what do these all have in common? 3 bonding domains. And then again, notice that their molecular geometries are determined by the number of bonding and non-bonding domains. You guys good? Yep. Last one. 2 objects around a central point. Let's see if my board does better. So guys, let's go. Oh, come on, give me that. Okay, central point. There we go. Draw. Really? Draw a circle. Switch colors. So guys, if I put 1 point there, where do I put the other point to get it as far away as possible? On the other side. And when we connect these, what is that angle? 180 degrees. What if we make it 3-dimensional? Doesn't change anything. So what is the angle? 180 degrees. And what do we call 3 points that are all in a line? Call it linear, not straight. Guys, straight means 2 points and no angle. Linear means 3 points and a 180-degree angle. So let's look at our let's look at our one example of a linear molecule, and that's going to be our good friend carbon dioxide. So guys, CO2 looks like this. You've drawn it before. Did you get it? So guys, we've got our central carbon right here. How many domains are on the central carbon? 1, 2. But how many of those domains are bonding domains? Both of them. How many are non-bonding domains? None of them. And guys, carbon dioxide looks like this. Oh my gosh, it's linear. That's the point. They're all in a straight line, and you can see the 180-degree angles. So the angle in this is 180, and the molecular geometry is also linear. Now guys, again, notice that I left off the example of one bonding domain, because again, that would be straight, and there would not be an angle. You guys good? All right, so what are we going to do with this? Please don't try to write this down. Just play along at home. So guys, here's what's going to happen. These are the instructions for your homework. Draw the Lewis dot molecular structure. You've done that before. We've done that for 2 days. But now, guys, this changes. The additional requirement is no longer count the shared and lone pairs. The requirement now is identify the domain in molecular geometry and the angle around the central atom. So guys, here's what you're going to want to do. For now, have this at the ready, your decoder key, with the understanding that you won't be able to use this on the test. You need to know these. Okay, so guys, here we go. PBr3. Oh my gosh, NO2. And look, we just drew the Lewis dot structure for PBr3. So here's what you now need to do once you've got the Lewis dot structures drawn. You need to identify, oh, it didn't come in stages. Oh, man. All right. You need to identify you need to identify the domain in molecular geometry and the angle. So here's how you do it. Guys, take a look at the phosphorus. How many domains are on the phosphorus? 4. So what is the domain geometry if it's 4? Tetrahedral. Now, how many, and so what that means then, guys, is that places you in this top table, right? Now, how many of those domains are bonding domains? 3. So, if 3 of the domains are bonding domains, what's the molecular geometry? Trigonal pyramid, and the angle is less than 109.5. You get the idea? Okay, so now let's look at either one of these oxygens. Let's do the one on the left. How many domains are on the oxygen? And be careful, guys. How many domains are on here? 1, 2, 3. So 3 domains is trigonal planar, right? Now, how many of these domains is bonding domains? 1. And so you'll notice that that is not on the table, because anytime you have one bonding domain, the name of the molecule is straight and the angle is undefined. Yep, you got it. Is that okay? And then, guys, finally here, take a look at the carbon. How many domains? 2. So that means the domain geometry is linear. They are both bonding domains, so the molecular geometry is also linear. And what's the angle? 180. You got the idea? Okay, so guys, again, what you're going to do is you're going to draw these Lewis dot structures, and then you are going to identify the domain in molecular geometries. Then, guys, when I see you on Thursday, we'll grade this, and then we'll get you model kits and really let you play with them. Go.